So greetings. So welcome to today's class. So let us briefly recap what, and then we will go forward, and then do further analysis of the linear bicycle dynamic model. So if you recall, we were considering the bicycle model, and then we essentially wrote down the equations of motion. We considered constant longitudinal speed, and then we considered low angle assumptions, and also a linear tire model to relate the lateral force and the slip angles. So after all these assumptions, we put everything together, and then we got two equations, which were second order ordinary differential equations, one in y and another in psi. So this is where we stopped, right? So, and then I gave a homework where I asked you to express this in the state space form, and also get the transfer function relating y and delta and psi n. Okay, so that's where we are. So the equations T1 and R1 put together constitute what is called as the linear dynamic bicycle model. Okay, so in today's class, let us analyze this further by representing the linear dynamic bicycle model in terms of the side slip angle beta and the yaw rate delta R. Okay, so let us start that analysis in today's class. So what we're going to do is that we are going to represent or rewrite the same model in terms of side slip angle beta and the yaw rate R. Okay, so these are the two parameters that we will be looking at. Okay, now what are these parameters, right? So as we know, if we look at the center of mass, right, which we labeled as point C. Okay, so let's say this is my longitudinal axis X, okay, which is fixed to the vehicle body. And as we are aware, at the point C, which is the center of mass, the velocity vector is going to be at an angle beta to the longitudinal axis. Okay, so let me draw the velocity vector at the center of mass V, and it is going to have two components, Vy, which we called as y dot, and then Vx, right, which is a longitudinal speed at the center of mass, and the angle which is made by the velocity vector with the longitudinal axis of the vehicle is what is called as the side slip angle beta, right? And what is the yaw angle? The yaw angle is the angle made by the longitudinal axis with the globe. Okay, so if you consider a global inertial frame of reference, which we call as capital X, capital Y, the angle which is made by the longitudinal axis of the vehicle with respect to the capital X axis is the yaw angle. Okay, so consequently, beta is the side slip angle. Yaw rate T is nothing but the rate of change of the yaw angle. So yaw rate, which is denoted as R of T, is nothing but psi dot of T. Okay, so that is the yaw rate. Okay, and beta is the side slip angle, as we know. Beta is going to be the side slip. All right. So now we are going to rewrite the governing equations T1 and R1 in terms of these two quantities. Okay, so that's what we are going to do. Before we do that, let us look at a few facts. If you look at this right angle triangle that we have drawn here, tan beta is going to be equal to Vy by Vx. So Vy we alternatively write as y dot. So Vy is nothing but y dot, okay, as per our notation. So we are essentially writing tan beta to be y dot by x. And once again, we are going to use a small angle approximation, considering small values of beta, okay, small angles, small side slip angle. We can immediately say that tan beta could be approximated as beta, and that is going to be implying, beta is going to be approximately equal to y dot divided by dx. Okay, so this is an important relationship. So this essentially implies that y dot of t, I'm just writing parenthesis t just to make a point, can be written as Vx times beta of t. Okay, so Vx is constant. Please remember that. Okay, so y dot becomes equal to Vx times beta of t. And this implies y double dot of t, which is the lateral acceleration, becomes equal to Vx times beta dot of t. Okay, so please note this one. Okay, so this is important. So that is point number one. And similarly, since r of t is the yaw rate, which is psi dot of t, r dot of t is going to be equal to psi double dot of t, okay, which is the yaw acceleration. Okay, so the derivative of yaw rate is the yaw acceleration. Okay, so let's keep both these equations in mind. All right. So now we are going to answer the question as to how do we rewrite the dynamic bicycle model using the yaw rate and the beta angle. Sorry, the side slip angle. Okay, so the that we are going to ask ourselves is that, like, how do we rewrite T1 and R1? Equation T1 denoted the equation of motion for translation. R1 was for rotation. Okay, in terms of beta of t and r of t. Okay, so that's what we want to do. So this is the question we are going to answer. So let us go back to those equations. Please keep these two equations in mind. Okay, the equation for r, beta, and y double dot and r. Okay, so if we keep this in mind, let's go back to the equations, right, that we consider. So let's first look at T1. Okay, so y dot, if you recall, now we can rewrite this as Vx times beta. Okay, because y beta is essentially y dot by Vx, right, for small angles. So we are essentially replacing y dot with Vx times beta. Okay, and psi dot is going to be equal to r of t. Okay, and y double dot t, one can write it as Vx times beta dot t. That's what we just wrote down. Okay, so I'm not doing anything other than, like substituting whatever we just derived, like for the variables in equation T1. Okay, so that's all we are doing right now. Similarly, we go to equation R1, like psi double dot is nothing but R dot. Okay, y dot, once again, is going to be equal to Vx times beta. And psi dot, as we know, is the yaw rate, RT. Okay. So we can see that, like we are essentially rewriting T1 and R1 in terms of the yaw rate and the side slip angle. Okay, so that's what we are doing. So consequently, let me go back and then rewrite these equations. But I hope it's clear what I am doing, right? So we have made some simplifying assumptions, and then like we are replacing y dot, y double dot, psi dot, and psi double dot in terms of beta, beta dot, r, and r dot. Okay, that's all we are doing. Okay, so and let's see what happens. So if we go down, like now, what happens? So equation T1 becomes following. So if I look at the equation of motion for translation, it can be written as the following. Okay, so y dot will become Vx times beta dot t. That's going to be equal to 2c alpha f divided by m delta t. Okay, and minus, okay, 2c alpha f plus 2c alpha r divided by m times Vx. This is something which we already had. But now what we are going to do is that like we are going to rewrite y dot as Vx times beta t. Okay, so that's the substitution we are doing. Okay, that is one. And then we have Vx plus 2c alpha f Lf minus 2c alpha r Lr. Okay, the whole thing divided by m Vx. Okay, this multiplies psi dot, which is now r of t. Sorry, I ran out of space there, but I'm just writing r of t there. Okay, so that's what we have. And one immediate simplification that we can do is that like this Vx cancel out, and I divide both sides by Vx. Then what happens? You know, like we get an expression for beta dot. Okay, so this gives us an evolution equation for the side slip angle. So beta dot of t will now become 2c alpha f by m delta t minus 2c alpha f plus 2c alpha r, right, divided by, of course, I have to divide both sides by Vx, right? So this becomes mVx. So this also becomes mVx times beta of t, and minus, if I take Vx, divide by Vx throughout, I will get Vx will cancel off within this bracket. So I will get 2Cl1 plus 2C alpha Lf minus 2C alpha Lr divided by m times Vx square, okay, times R of. All right, so this is what happens to the first equation. So we can see that we have rewritten the equation for translation, which was an equation in y double dot t as an equation in the time derivative of the side slip angle beta. So let's call this equation as some T2. Okay, so I'm calling this equation as T2. Just to denote that, we have rewritten the equation of motion for translation in a slightly different way. Okay, so that's all we are. So similarly, R1 can be rewritten, right? So R1 can be rewritten as follows. Okay, so I leave this as an exercise to you. We have already substituted it. You just need to simplify it a little bit. So we will get an expression for R dot P. R dot P will become 2C alpha F LF divided by I is a delta T minus 2C alpha F LF minus 2C alpha R LR, whole thing divided by I is a. This multiplies beta of t minus 2c alpha f Lf square plus 2c alpha r Lr square divided by Iz Vx. Okay, this multiplies. Okay, so this is the second equation. Okay, so this once again very straightforward. We have already done the substitution. Like you just need to rewrite in that form. Okay, so nothing which is a very complicated operation. It's a very simple algebraic operation that we are doing. Okay, so okay, very simple algebraic operation which we have done to essentially get the second equation, which is now we label it as some R2. Okay, this is again the equation of motion for rotation, But only thing is that like now we are rewriting in terms of the yaw rate. Okay. So that's all we have done. I hope it is clear what we have done, right? So yeah. So once again, please stop me whenever there is a question. Okay. So let us now write T2 and R2 in the state space representation. Okay. So see, things have become a little bit simplified now, right? So what was previously two second order ordinary differential equations in y and psi have become two first order ordinary differential equations in beta and r. Okay, so that is the simplification we have got, right? So I think that's something which we need to recognize. Okay, so let us write T2 and R2 in the state space representation. All right. So let's try to do this. Okay. So and we will see what happens due to this. Okay. So if we write T2 and R2 in the state space representation, x of t, let's say we call that as a state vector. So if you recall the state vector, state space representation, we need to write x dot equals ax plus bu, right? So now we directly have two first order ODEs, right? Which essentially govern the evolution of beta and r. So what we do is that like we just directly take them and then write them. So and observe that the state vector x of t is going to be, let's say, a column vector containing beta and r, okay? And the input, like is the steering angle delta, okay? So that's what we are going to have, all right? Okay, so now with this selection, what happens? We just need to combine these two equations and write it as one equation. Okay, so let's do that, and then like I'm going to do some analysis, and then like we will observe something interesting. So we essentially now combine the two first order ODEs in beta and r. So we get beta dot and r dot of t. So what will be the entries? Okay, so let's write down the entries that come about. So please note that beta dot is going to be minus 2c alpha f plus 2c alpha divided by mvx times beta t. So the first entry will be the minus 2c alpha f plus 2c alpha r divided by mvx, okay, times beta. So please note that, see, at first glance, this bit unwieldy, but please bear with me for some time. We will essentially write down these expressions, okay? And then the coefficient which multiplies r of t is minus of 1 plus 2c alpha f lf minus 2c alpha r lr divided by m vx square. Okay, so that is the coefficient which multiplies r of. Okay, so this multiplies beta of t and r of. These are the two coefficients of beta and r. Okay, so we are slowly forming the state matrix, right? As we now coming to the equation for r dot, right? What do we have? What is the coefficient that multiplies beta of t? Minus 2c alpha f minus 2c alpha r l divided by I z. Okay, that's the coefficient that multiplies beta of t. And the coefficient that multiplies r of t is going to be minus 2c alpha f lf square plus 2c alpha r lr square divided by I z dx. Okay, so this is the matrix which multiplies the state vector. Okay, so that's the state matrix. Now, as we know, the state phase representation is x dot equals ax plus bu, right? So we need to essentially rewrite the terms corresponding to the terms that multiply delta. Okay, so that is still left. So if you go to the first equation for beta dot, what is the coefficient that multiplies delta? It's 2c alpha f by mvx, right? It is this coefficient. Okay, so that's what we are going to write. Okay, so we will essentially go and write 2c alpha f divided by m times vx Okay, that is one coefficient. Then the coefficient that multiplies delta in R dot is going to be 2 C alpha F LF by IZ. Okay, so that's the second one. So essentially, C alpha F LF divided by IZ. Okay, so that is the coefficient that multiplies delta in the equation for R. Okay, so this is the state equation. Okay, so please recall the state equation is of the form x dot t is equal to axt plus bu. All right, so that's what is the state equation in the state space representation, right? So that is something we need to remember. So consequently, we have rewritten in terms of the state space representation. So this is our derivative of the state vector dot. This is the state vector x. This is the input matrix. Sorry, not input matrix. State matrix A. This is the input vector B. And in the system, the steering angle is the input u of t. Okay, so we can immediately see that we have represented the governing equations in the standard state space form. Okay, so now I hope all of us can connect the dots, right? See, we have been essentially deriving various equations of motion, right? And we have had a very long derivation. Ultimately, what we are doing is that like we are going to put it in the state space form and do the stability analysis and connect it to cornering stability. So now we will also get a flavor of why we studied the initial part on dynamic systems, right? So the transfer function, the state space representation, and so on. Okay. So we, as we know, like when we studied about the state space representation also, right? For the stability of a system, we need the eigenvalues of the state matrix to be in the left of complex plane, right? So that is a condition that we require. So consequently, we want to ensure that, we are able to analyze this system for its stability by looking at its eigenvalues of the state matrix. Okay, so we are essentially going to do that analysis. Okay, so I hope it is clear in which direction we are proceeding. And as we know, the eigenvalues of the state matrix are the roots of the characteristic polynomial determinant of lambda I minus a. Okay, so we are going to calculate determinant of lambda I minus a. Okay, so let us do this. So what will be determinant of lambda I minus a? Once again, it's going to be a little bit elongated because we have all these symbols, but then please bear with me. Okay. So what is determinant of lambda I minus a? So lambda I will be a 2 by 2 matrix in this case, right? Whose diagonal elements will be just lambda. And then we need to subtract this 2 by 2 matrix from lambda I, right? So what will happen? So we will have lambda plus 2c alpha f plus 2c alpha r, okay, divided by mvx. Okay, so minus became plus, right? So because we are essentially having lambda I minus a, okay? And then the second term on the first row will become plus 1 plus 2c alpha f lf minus 2c alpha r lr divided by mvx square. That is the second term. Then what will happen? Coming to the second row, once again that minus term will become plus. So we'll get 2c alpha f lf minus 2c alpha r lr, okay, divided by iz. Then finally we have lambda plus 2c alpha f lf square plus 2c alpha r lr square divided by iz x. Okay, so these are the 4 terms. So now we essentially have determinant of lambda I minus a. And how do we calculate the determinant of the 2 by 2 matrix? We just cross multiply, right? First, we essentially cross multiply these diagonal terms and then take the product of the off diagonal terms, subtract the two, right? So we get the product of the diagonal terms. From that product, we subtract the product of the off diagonal terms, right? So that's what we will be doing. So if we do this, I'm just going to write down what we will ultimately get. I leave this to you as a simplification, as an exercise to you. We will get a second order polynomial in lambda. So it will be lambda squared plus the coefficient of lambda is going to be the following: 2c alpha f plus 2c alpha r divided by mvx plus 2c alpha f lf squared plus 2c alpha r lr squared divided by izvx. Okay, so this is going to be the coefficient multiplying lambda. Then we are going to have a constant term. So what is this constant term? It's a rather long term, so that's why I'm writing in the next line. So the constant term is going to be 2 alpha f plus 2c alpha r multiplying 2c alpha f lf square plus 2c alpha r lr square, okay, divided by m I is a vx square, okay, that is one term. Then we have minus 2c alpha f lf minus 2c alpha r lr divided by I is a multiplying 1 plus 2c alpha f lf minus 2c alpha r lr divided by m dx squared. Okay, so a rather long expression, right? So please bear with me. We will be done in maybe another 5 minutes, okay, with this analysis. Okay, so this is what we have. Okay, so this is the characteristic polynomial of the system. Okay, so please note that the characteristic polynomial is of form characteristic polynomial is of form it's a quadratic polynomial, right? It's a second order polynomial. It's of the form a naught lambda square plus a1 lambda plus a2. Okay, of course, here a naught is 1, okay, plus 1. So what is a naught? A naught is the coefficient of lambda square, right? So that one can immediately observe that it's going to be plus 1, right? So we can immediately see that a naught is 1. What is a1? A1 is the coefficient of lambda, and we can once again observe that a1 is greater than 0. Okay, so although we don't know the numerical values of c alpha f, c alpha r, m, vx, lf, lr, and so on, if you look at the expression per se, right, all the parameters that appear in the expression for a1 are all positive. So consequently, we can immediately say that a1 is going to be a positive number, right? Positive real number. I'm sure all of us can agree with it. Now, what is a2? A2 is this big expression. Okay, it's just a constant. Okay, so this is a2. Okay, so why am I doing all this, right? So I'm going to write down couple of important points. Okay, so for stability, so what is called asymptotic stability or stability, right? We require the eigenvalues of A eigenvalues of the state matrix, right? A to lie in the left of complex plane. Okay, so of course I should let me be redundant and then let me put all the eigenvalues. Okay, so it's so for asymptotic stability of the system, we require all the eigenvalues of the state matrix to lie in the left of complex plane. This is something which we are already learned. Now, what is the connection to our discussion? It so happens that if you have a characteristic polynomial of order 2, the necessary and sufficient condition for the second order polynomial of the form a naught lambda square plus a1 lambda plus a2 have both its roots in the left of complex plane LHP is that a naught, a1 and a2 must be non-zero and of the same sign. Okay, so that is the necessary and sufficient condition for stability. Okay, so I hope this is clear, right? So there are 2 points, okay, and we are going to establish the equivalence or connection between these 2 points. Okay, what is point number 1? We derive the characteristic polynomial of the state space representation by calculating determinant of lambda minus a, right? And that is of the form a naught lambda squared plus a1 lambda plus a2. Okay, now we see that, like for stability, we already know that the eigenvalues of the state matrix should be both in the left of complex plane, right? So that is something which all of us know. So now, in order to check that, like we need to solve for the eigenvalues of the state matrix, right? But then we can, we already see that, like it's a very, very big expression, right? So, but then, however, we don't want the exact values of lambda, right? In terms of the various system parameters, we only want to find some condition on the system parameters such that our eigenvalues will, both the eigenvalues will lie in complex. That's all we want. So the question is, how do we do that? So that's where another result comes into for our to our help. So it so turns out that if we have a quadratic polynomial of the form a naught lambda squared plus a1 lambda plus a2, the necessary and sufficient condition for this quadratic polynomial to have both its roots in the left of complex plane is that a naught, a1, a2 must all be non-zero and of the same sign. Okay, so if we apply this result to our problem, please note that a naught is non-zero, it's positive. A1 is also non-zero, also positive. So what is the condition on A2? It should be also positive. Okay, see, please note that the mathematical condition doesn't say positive. It only says all the 3 coefficients A0, A1, A2 must be non-zero and of the same sign. Either all 3 are negative or all 3 of them should be positive. In our case, A0 and A1 are already deemed to be positive. So, thus, we can immediately write for asymptotic stability of the cornering dynamics, for asymptotic stability of the cornering response, analyzed using the bicycle model, okay, we require A2 to be greater than 0. Okay, so we require A2 to be greater than. Okay, so what is this A2? It's this big expression that we have written down. Okay, so I'm just now going to leave you with an exercise for you to do. So this is an optional exercise. Okay, simplify. You don't need to submit it. I would strongly advise you to do this, okay, so that like you get a good insights into what is happening. Simplify the expression for A2 to obtain the following. to obtain L plus Vx squared by G times mg LR divided by 2C alpha F L minus mg LF divided by 2C alpha R L. Okay, this is greater than 0. Okay, so one can simplify this condition. Okay, so please do that as an exercise. Okay, so I hope it's clear what I'm asking you to do, right? So just to recap, we have this characteristic polynomial associated with the linear bicycle model to be of the form a0 lambda squared plus a1 lambda plus a2. For asymptotic stability, we require a0, a1, a2, all three to be non-zero and of the same sign. And we already know that a0 is plus 1. A1 is anyway positive. So A2 should be positive for asymptotic stability. Okay. So I am asking you to simplify A2 greater than 0 to get this condition. Okay. So you can do this as an optional exercise. So please do that. Okay. And I'm going to simplify this a little bit further. Okay. And then like do some analysis. Okay. Any questions? So this is a rather long derivation. So please do practice it once. And if you have any questions, please feel free to ask them. Okay, like later on. So I'm just drawing a very simple schematic.
Sir,
Just to, yes, please.
Yeah, you're saying like a whole derivation, right, sir? Not the
Which one?
whatever you're just mentioned it, like a whole derivation,
Yeah.
right?
Whole entire derivation.
Okay, sir.
I'm just suggesting that you practice the entire derivation. Okay.
Okay, sir.
Yeah. Okay. So now this is something which we have already. Yeah. Any other questions before we proceed further?
Sorry, sir. This A1, how did we directly say it is greater than 0? Like because of the.
So good point. Let me recap that. So why is A greater than 0? Please note that A1 is 2C alpha F plus 2C alpha by M Vx. C alpha F, C alpha are all positive. M is positive, Vx is positive. So I'm sure you agree that that ratio is positive. Right?
Yeah.
Same comment for the second term also. So we have addition of two positive numbers, which is positive. Okay.
Okay.
Right? Okay. Good point. Okay. Yeah. So please practice the entire derivation once, like and do the simplification. Okay. So this I'm giving this to you as an exercise. As I mentioned, you don't need to submit this, but then I would strongly advise you to do this. Okay. So this will involve some more algebra. So please do. All right. Okay. So I'm just drawing a stationary vehicle, to essentially convey some points. So let us say this is the weight of the vehicle. These are the normal loads at the front contact point and the rear contact point. And let's say this is our load. Okay. So front contact point, we call it as A, rear contact point, we call it as B. Okay. And the wheelbase of the vehicle is, wheelbase of the vehicle is capital L. And as we know, we mark L1 and L2 as the distance of the center of gravity from the front wheel contact point and the rear wheel contact point. Okay, so these are some important things. Okay, so now why did I draw this? Okay, consider the vehicle to be at rest. So we just want to simplify this expression a little bit further. So if we take moments about point A, if we take moments about point A, what's going to happen? We are essentially going to get W times L. So, okay, this I'm calling as LFLR, right? Sorry about that. There's a small change. I'm very sorry. Okay. So, in this derivation, we are calling it as LFLR. Okay. So, yeah. Okay. So, we will have W times LF. Okay. To be equal to WR times capital L. So this will imply that the static load on the rear, which is WR, is going to be equal to WLF L, which I can rewrite this as mg times LF divided by L. Okay, so I hope this is very straightforward, right? So we are already aware of this. I'm just recapping this. Okay, so this is the expression for the static load on the rear wheel. Okay, so this is the normal load on the rear wheels. Okay, similarly, one can get an expression for the normal load on the front wheels. Okay, so what is that expression? We can get that by taking moments about point B. Okay, so we can, of course, use another expression also, just to do it in a slightly different way. We also know that this is stationary, so W equals WF plus WR. So the static load on the front wheel is going to be equal to W minus WR. Of course, one could also take moments about point B and we will get the same expression. We will see that we will get it as WLR by L. Okay, because LF plus LR equals capital, right? So, and then like this, we can rewrite as mg LR divided by capital. Okay, so okay. So if we look at this expression, this is the expression for the normal load on the rear. Sorry, the normal load on the front wheels. Okay, so this is the expression W for WF. Okay, WF is the normal load on the front wheels. So we are almost getting to the end of this rather long derivation. Okay, just a few more minutes. Now, why did I do this? Okay, so let's go here, this constraint, and look at this. So please look at what I am circling. Okay, this term, which essentially I have circled, right? R by L is nothing but WF. Similarly, in the second term, which is GLF by L, that is WR. Okay, so consequently, we can see that the condition for asymptotic stability can now be rewritten. Okay, thus, write it carefully. Thus, the condition for asymptotic stability can be rewritten as the following. Okay, so what is that? We can rewrite as L plus Bx squared divided by G times WF divided by 2C alpha F minus WR divided by 2C alpha R. Okay, this is greater than 0. So you can see that after all this derivation, this condition has become very simple in structure, right? So I just substituted for WF and WR, right? And we have got this expression. Now, this within square bracket is what is called as the understeer gradient, okay? Denoted by K subscript B, which is going to be equal to pi 2C alpha F minus WR divided by 2C alpha R. This is what is called as the understeer gradient or understeer coefficient. Okay, so this is what is called as the understeer gradient. Some people call it as the understeer coefficient also. Okay, so gradients or coefficient. Okay, in some references, you would also see that this is denoted by K subscript US. Okay, So finally, like using the linear dynamic bicycle model, the condition for ordering stability becomes the following. Okay, through this definition, we get it as L plus KB Vx squared divided by G to be greater than. Okay, so this is finally the condition for cornering stability using the linear dynamic bicycle model. Please note that. Okay, so that is something which is very, very important. Okay, so we can't just interpret cornering stability in a very broad sense. This cornering stability, provided we can analyze the cornering maneuver using the linear dynamic bicycle model, such that all the conditions are satisfied, that we make during the assumption of this derivation. Okay, so this is a rather long. I will stop here, and then we will interpret this condition, and then define notions of understeer, oversteer, neutral steer, which are all very important for cornering performance. But I will leave you with this fact that the steer gradient is dependent on load distribution and cornering stiffness of the tire. Okay, so these are the two important aspects that affect the steer gradient. Okay, so it's not only the total load, it is the load distribution between the front and the rear tires. Okay, and the cornering stiffness of the front and the rear tires that influence the understeer gradient. All right. Okay. So I will stop here for today, and then we will continue here in the next class. Are there any questions before I close today's session? All right. So let me recording.